lecture starts, I'll ask Paulo da Veiga, who is our host, to say a few words about the event.
Thank you, Roberto. So I would like, on behalf of my director, to welcome all of you and to say that we made our best efforts to have a well-organized school. If this is not the case, I apologize for this and ask you sorry. You see on the blackboard, there is data concerning our network. There is another room, which is number 3009. I'll show you when we are in the first coffee break. That's a place you can be by yourself. There's a blackboard there. There's network everywhere. And the password and the user ID that I gave on the blackboard works fine, should be fine everywhere, okay? So I hope you have a very nice week and wish you a very good EBP. Thank you.
So let me introduce now our first speaker. Well, actually, the first lecture of the mini course by our own Sergei Popov from the University of Campinas, and he'll be talking about the Lyapunov functions for random walks.
Sim, sim. Tá, tudo bem. Eu deixo aqui, tá tudo bem. Bom, obrigado, Roberto, por me convidar aqui. Agora eu peço desculpas por... Just, I'm kind of caught cold, so you see, I hope that's not a problem for you. And, well, let me erase this. Let me not erase this because it's something important, not during my lecture, but afterwards. And, well, so this will be a mini course about the method of Lyapunov functions applied to countable Markov chains with discrete time. So there is some lecture notes in the internet. This is underline. Okay. So, well, I made a joke. It's not lecture notes. It's really a book which we just wrote with Misha Menshikov and Andrew Waite. So everybody is free to download and use it. Of course, I will not cover everything, but I will cover some things. And in case you find any mistakes and you have suggestions, comments, etc., just send them to me or to Andrew, to Misha, because this is not yet the really final version. So all comments are welcome. Now, well, let me maybe start. start with the question of recurrence and transience of countable Markov chains. Well, I guess everybody knows what is it. Recurrence means that almost surely you will return to your starting point, which is equivalent that almost surely you will visit all the states of your countable Markov chains infinitely many times. And, well, transience means not recurrence, and of course, any Markov chains which we consider here are irreducible, so they have just one equivalence class, so all states are of the same type. Okay, and transience means that you start somewhere, and with positive probability, you will not return to your initial position. Well, now you have this argument that recurrence is equivalent to the fact that the expected number of returns to the origin is infinite. Well, that's because if it was this number of returns is geometric. So each time you return, you are in the same situation. Then you either return again or not. So a geometric random variable with p less than 1 has with p between 0 and 1 has finite expectation, and so recurrence is equivalent to this. Sum k from 0 to infinity, transition probability in k steps from a fixed site to a fixed site which we call 0 is infinite. So, well, this is just the expectation of number of returns, because if you think about probability as an expectation and send the expectation out of the sum, you will see that it's just really the expected number of returns. Okay, so this is what recurrence means. Now, let's recall a very classical result called Pauli's theorem. So first, we define this object called simple random walk on ZD. Just from each side you go to neighbors with equal probabilities, and well, with probabilities actually 1 over 2d, right? And there is this famous Pauli's theorem that this simple random walk in d dimension is recurrent when d is less than equal to 2 and transient when d is greater than equal 3. So there is also a equally famous Kakutanis interpretation of this fact, which I will not write down, but for some reason, which says that a drunken man will return home almost surely. So it corresponds to the recurrence of simple random walk in dimension 2, but a drunken bird will eventually be lost forever. Okay, that's why birds don't drink vodka. Well, so now let me quickly recall the classical Polias proof of recurrence. Well, you need to see if this holds, right? So, of course, this can be positive only for the case when k is even. So I will just calculate P00 to, let me change the index to n. So I will write the formula and then explain. So it's 1/4 to 2n times sum k equals 0 n. Sorry. You have to okay. To k 2 n minus k times 2n to k. Okay, this is some. This is a multinomial coefficient, in fact, but I prefer to write it this way. So now, to explain this, first, observe that there are 4 to 2n different trajectories up to time to n. Well, because on each step you choose the direction with probability 1/4. So this is just the weight of each trajectory. Now, you want your trajectory to return, to be in the origin, to be at the origin at time 2n. Now, if you want to be there at time 2n, you need that the number of steps up should be equal to the number of steps down, and the number of steps to the right should be equal to the number of steps to the left. Okay, so I just say that, okay, let 2k be the number of steps in the vertical direction. Okay, so this binomial coefficient here is just the number of different ways to choose the positions when your random walk will jump in the vertical direction, either up or down. Now, between these 2k vertical steps, you need to choose the position of steps downwards. So this is this binomial coefficient, and between these 2n minus k steps in the horizontal direction, you need to choose n minus k positions for steps to the right, for instance. Okay, so this is an exact formula, and we simplify it a little bit, do something to n. Now I write this sum, so it's 2k factorial, k factorial square, times 2n minus k factorial n minus k factorial square, times 2n factorial 2k factorial 2 n minus k factorial. So I cancel something. Okay. Then I bring this to n factorial out. And actually I want to divide it by, okay, to n factorial is out. I divide it by n factorial square and put this n factorial square here. Okay, then what we have here is n factorial times n factorial over k factorial times k factorial minus k. Which is 1 over 4 to n. Binomial coefficient to n, sum. Now here, okay, from 0 to n. Now here we have actually a binomial coefficient nk squared. But I would like to write it a bit different. So this with this and with this is binomial coefficient nk, and this with this and with this would be binomial coefficient n minus k. Of course they are equal, but for some reason I prefer writing it this way. Now there is a nice combinatorial identity that this sum is actually just equal to this binomial coefficient here, because it's quite elementary argument. You have to you want to choose n persons from a group of 2n persons. Of course, the number of ways to do it is this. Now, assume that in your group of n people, there are, in your group of 2n people, there are n men and n women. So, and you want to choose n, a subgroup of n people from there. So first you can fix a k and try to choose your subgroup in such a way that there are k women. So this is the number of the ways to choose k women, and this is the number of ways to choose n minus k men. And you kind of consider all the possibilities and sum them up. So this should be equal to this, and we arrive to the following formula: 1 over 2 to 2n times binomial coefficient to n all squared. So we see this is really luck that we could write it this way. Okay, now you use the Stirling formula that n factorial is equivalent to square root of 2n pi n over e to n, and you do the calculations, which I think I will not do here, to see that this is essentially equivalent to 1 over pi n, right? So, well, probably most of you already seen this calculation, but okay. If not, then I leave it as an exercise. Now, let's go back here. You see that essentially we have a sum of the harmonic series, which diverges, you know. So, since the harmonic series diverges, we get the recurrence of simple random walk in 2 dimensions. Well, now, why this proof is good? Because it's nice and beautiful and ingenious. Why this proof is bad? Well, because it's ingenious. Which means that we really had luck that we could do all these calculations and arrive to these nice closed form expressions and use Stirling formula to come to the answer. In dimension 3, for instance, well, in dimension 3, you will obtain a kind of similar formula, but you will not be able to really simplify it. You see, this is just probability of return in 1 dimension squared, right? It's in 1 dimension to return to be at the origin at time 2n, you have to do n steps to the left and n steps to the right. So you see here in 2 dimensions, by miracle, it's 1-dimensional return probability squared. Unfortunately, in 3 dimensions, it will not be true because the components, with discrete time, the components are not independent. And you will be left with a task of estimating some expression with sums and so on to prove that essentially it would be of order 1 over n to 3 over 2, which converges. But you see, it's usually we don't show these proofs to the students in order not to frighten them. So, it can be done, but it's not as nice as this one. Okay, there are other beautiful proofs. Sorry. So you see, this proof is nice and ingenious, but suppose that I change the transition probabilities in just 1 point. For instance, in the origin, it will go up and down with probability 1 over 8, 1 over 8, and left and right, 3 over 8 and 3 over 8. And in the other places, just the same. Well, you will not be able to really write such a beautiful expression. Or suppose that you have, you modify a little bit your random walk. You want it to go also, you wanted to do also diagonal steps with equal probabilities. Again, this will not work. You will not be able to write a simple expression for the return, for the probability to be at the origin at time 2n. By the way, here it's not periodic, so here you even have to calculate it for all n. So you see, the problem is that it is not robust. Now, there are other proofs of this fact, and the most famous of them is the proof through electrical networks. So there is a very, very classical book of Doyle and Snell called Random Walks. And electrical networks. Well, it is available for download. You can, they just put it in the archive, so you can download it free of charge. And if you never read it, it's absolutely mandatory that you read it now, because it's really, really nice and classical and beautiful. Okay. And it's not difficult. It's even pleasant to read it. So then, basically, when you want to prove recurrence using electric networks method, you first consider this lattice, thinking that each edge of the lattice is a conductor with a resistance equal to 1. Well, now you grosso modo you do the following. You put a battery with one contact at the origin and the other contact at infinity. Well, you understand, right? And ask, is there a current from the origin to infinity? In other words, the current, so it's 1 volt. The current will flow if the so-called resistance between 0 and infinity is finite. Okay, by Ohm's law. Now, you define something called effective resistance, which is for physicists it would be just resistance, and you prove that recurrence is equivalent to the fact that the effective resistance is infinite. Now, when you deal with electric networks, there are some things that you can do with networks kind of intuitive way. For instance, if you have a network, something like this, so these are resistors, and you are interested in what is the resistance between this point and this point. Well, what do you think? If I cut one edge here, the resistance will increase or decrease? Well, obviously, if I cut something, it will be more difficult for the current to pass. On the other hand, if I add another edge, if I kind of short circuit two edges by putting between them a wire with resistance 0. Then I can only decrease the effective point and this point. It's very intuitive, and even more, it cannot be proved. Now, with this kind of considerations, you can kind of short circuit edges here, then edges here, etc., and then you will be left with a kind of you will obtain something for which you can really calculate the resistance, and then you will obtain the recurrence essentially again because the harmonic series diverges. Okay, so the harmonic series will come out again in this argument. Well, again, this proof is beautiful, but it has again a drawback because you can do such things only for reversible Markov chains. Right. So it's very easy to make a Markov chain non-reversible. Even well, if you have two sides such that you can go in one step from one side to the other, but you cannot go in one step from this side to this, then you can be sure that your chain is non-reversible already. So it's really easy to spoil reversibility. So the idea of this course is to make an introduction to more robust methods which will allow us to prove recurrence, transience, and other things in a way which is not easy to break. In a way which applies to not only to these special random walks, but to more general class of Markov chains. Okay. Now, let me do a calculation. So let's, we have now simple random walk in ZD, d greater equal than 1. And so let Sn be the simple random walk. And let Xn be the norm of Sn. So this is Euclidean norm. It's square root of Sn scalar product with Sn. Now, I would like to calculate so this Xn is a one-dimensional process for any d. So I would like to calculate, well, how does it behave? what is, how does it look like, this one-dimensional process? Well, let's try to calculate the first and second moments of the increments of this process xn. So I want to calculate expectation of xn plus 1 minus xn given Sn equals to x. And I also want to calculate expectation of xn plus 1 minus xn square given Sn equals x. Okay? Sorry, xn is already, xn is the norm already. Okay, so how shall we do this? How shall we do this? Well, so here xn is just norm of x. So xn plus 1 is, is x plus some unit vector. So let E be a unit vector. Let's write down what is this thing here, x plus E minus x. Well, this is what? This is square root of x plus E times x plus E minus norm x. Now, I will bring x out, and here I just multiply, so it will be x square minus, plus 2x times E plus 1 over x square all to 1/2 minus 1. Agree? So this thing here is what is 1 plus 2x times E plus 1 over x squared. Okay, so we are interested now in the behavior of this thing when x is large. So when x is large, this term here is small. You have x squared in the denominator, and here is just see. So we can use the Taylor expansion for this 1 plus something small to 1/2. So 1 plus something small to 1/2 is 1 plus something small over 2 minus this y square over 8 and plus terms of order y to 3. Okay. Okay, let's just put it there. It's an elementary calculation, but let's do it nicely. So it's okay. So this one will cancel with this one. Now this y over 2 will be what? 2 e times x plus 1 over 2 x squared plus minus this term here. So I kind of forget this one because so it will be 4 over 8, which is half, e times x square over norm x to 4 and plus terms of order norm x to minus 3. Okay. Agree? I think it's 2 here. Where is 6? No, this thing is for the 1 over norm x. Okay. Okay, so I think it's correct. Now, what about this expectation? So, to calculate this expectation there, you just think that this E is randomly chosen between the 2D unit vectors. Okay. So you will get that this term just disappears. Okay. This term, well, what happens with this term? Well, if you sum, if E1, ED are the coordinate vectors, and if you sum EJ times X squared from J from 1 to D, well, you will get just a norm of X squared. Okay, so just coordinate square here. So, okay, so this will become x squared over x to 4, so 1 over 2x squared. Yes, yes, this 2 disappears exactly because you have 2 sums like this. Finally, you get d minus 1 over 2d times 1 over norm x plus big O x minus 2, right? Half minus 5 to D, that's fine, yeah. Okay. Okay, so this is the first moment. Now let's calculate the second moment. Well, to calculate the second moment, first you observe that expectation of x n plus 1 squared minus x n squared given as n equals x. Well, this is just what this is. Sum 1 over 2d, sum j from 1 to n, x plus e. It's not good to put it here, sorry. So x plus ej square plus x minus ej square minus 2x square. Well, you just now open the parentheses, multiply, then this will cancel. Here you will have 1 minus, here you will have 2x times ej. Here you have minus 2x times ej. This will cancel as well. Only one here and one here will not cancel. There will be 2d of them, and so this is just 1. And now I use that x minus y square equals to x square minus y square minus 2x x minus y. Correct? Minus 2. Should it be plus, in fact? Y minus x, of course. Like this. No? I think now it's correct, no? No? Here, yes. No, it's correct. X square, yes, y square minus x square. Yeah. Now it's really correct. So think of y being xn plus 1 and x is xn. So expectation of this equals to expectation of this, which is 1, times 2x times expectation of this. Right? So after we calculate, we arrive to 1 over d plus big O of x to minus 1. I think it can be even x to minus 2, but let's not be perfectionists. Okay, so we calculated for this one-dimensional process, we calculated the first moment of its increment, which happens to be of this order, and also we calculated the second moment, which is constant. Now, this is good because a second moment is constant means that you kind of have nice random variable, which is not very random, but also not very deterministic. So this means that we have the right scale for our process xn. And the first moment happens to be, so if Sn equals to x, then if Sn is x, then xn is norm x. So you can rewrite this like expectation of xn plus 1 minus xn given xn equals to, I don't know, v is constant, which is d minus 1 over 2d times 1 over v plus terms of smaller order. Now, in this course, we will encounter such kind of processes many times. Where, so then, let me give, let's say, a loose definition. So, suppose now that x is just a process on R, in fact on R plus, and let's denote by mu1 of small x. Now this small x is just a number. mu1 of small x will be expectation of x n plus 1 minus xn, given all the history of the thing, and also given that xn equals to small x, and mu2 of x is expectation of the second moment of this guy, given the history and given xn is in x squared. So, by definition, so if absolute value of mu1 of x is of order 1 over x, and second moment is of order constant, we will call this stochastic process a Lampertis process. Well, John Lamperti was a very famous probabilist who did many beautiful things. But one of things that he did was he studied Markov chains on just one-dimensional, with where the first moment is of order 1 over where you are. Well, it can be negative, it can be positive, but this is the order, and the second moment is just constant. And well, I think he had 2 or 3 papers about properties of such kind of processes. Now, you see that the norm of simple random walk is a Lamperti process. So, tomorrow we will study Lamperti processes and see that it is really a nice kind of process in the sense that it is critical. It can exhibit very different behaviors depending on the relationships between these two guys. Okay, I think I shall stop here. Question? Questions?
So do we have any quick questions? Yes. Well, maybe not a quick question. Sorry?
The effective resistance of electric network is increasing in the resistance of each edge. It's intuitively obvious, you say, and you said it cannot be proved?
It can be proved.
Can be?
It really can be proved. Yeah.
Okay.
It's not only obvious.
Okay, thank you.
So if there are no more questions, let's thank Sergey again. And now we have a coffee break, I guess.
Yeah. I'd like
those
to tell you that we have to go up. The coffee break will be served on the ground floor of the library. The building you see in front of you is our library. And I would like to warn you that there's another event going on at this moment. It's a school in industrial mathematics. We are going to share the coffee break with them. Okay?
So,
Each one is going to pay for this portion for the organization. I just would like to warn you that there are wallets on the side of the seats, okay, on the black part, somewhere. Bem-vindo aqui. Vamos lá, Roberto.
Vambora. Deixa eu só dar uma olhada no vídeo.
Ei.